We just finished chapter 15. Chapter 15 talked about equilibrium. And now we're going into chapter 16. 16 talks about acids and bases. Now we've already mentioned and had chapters focused on acids and bases a little bit, but this one is going to look more specifically at, well, more in depth into acids and bases. And it applies to equilibrium because weak acids are a classic example of materials or chemicals that are in equilibrium. Okay? So after we go through our chapter of acids and bases, we're going to have a chapter about how equilibrium applies to acids and bases. All right? And so we won't have an exam after chapter 16. We'll have an exam after chapter 17. Okay. So let me make sure that this is done correctly. All right. So some of this will be review. If it's not, and you don't understand something, then you say, wait a second, I didn't quite understand that. Can you help me understand what's going on? That's what we do. All right. So here we have an example of an acid-base reaction. See how it follows the A, B, C, D pattern, right? Bases, strong bases, right, are ionic compounds. Sodium, metal, hydroxide, that's a polyatomic anion, right? So we have an ionic compound here. Now HCl hydrogen chloride, is a molecular compound. However, when it's placed in water, it behaves ionically in that it separates into its ions. Okay? Let me bring up this here and remind everybody what we're talking about when we say an acid. The general formula for an acid usually starts with a hydrogen ion, and the rest of it, like we'll just say A, meaning the anion, the rest of it, right? When you put this into water, if this is an acid, the general definition of an acid is a chemical which, when placed into water, dissociates to release the hydrogen ion. And then the rest of what's left will be over here. Okay? So an acid, molecular compound, however, when placed in water, it behaves ionically. Okay. Now, another way of thinking about an acid is to say that an acid donates a proton or a hydrogen ion, and that's what we talk about when we're talking about a proton. The hydrogen ion, also called a proton, because that's what it is, right? Hydrogen atom is, and we'll have this little review here real quick. Hydrogen atom, whoops, hydrogen atom without the minus sign there, just a hydrogen atom, one proton, one electron. Okay? When I remove an electron, meaning it has a positive charge now, the electron's gone and all that's left behind is the proton. So here is an acid placed into water, ionizes, and that proton is left behind to interact with water molecules, right? Just like the anion of the acid will interact with water molecules as well. Both of these charges will be stabilized by water molecules, right? Water molecules will stabilize this negative charge by with the hydrogen ends of polar molecules, right? So this is like a the positive end of the dipole on the hydrogen-oxygen bond will be stabilizing this ion. So we have an ion-dipole interaction. Here we have the same thing, an ion-dipole interaction, but it's the oxygen end this time. It's stabilizing the positively charged hydrogen ion. Okay, so we're familiar, hopefully, with this reaction between a base and an acid. All right. Again, one definition of the Bronsted definition is that the acid is the chemical that is donating the hydrogen to this reaction, while the base is the chemical that's donating the hydroxide ion, or the rest of the water molecule, because the hydrogen and the hydroxide ion come together to form a water molecule. All right? We also just have general dissociation of acids in water. So if you just have HCl, an acid, you can draw it in water like this and show that the water molecule will take that hydrogen ion, and so this H3O plus is essentially this hydrogen ion being being stabilized by the oxygen's negative end, right, of a water molecule, and then the leftover chloride ion, which is again stabilized by a cluster of other water molecules. And we want to be able to be comfortable and remember that you can draw the dissociation of an acid like this, HCl with the water molecule, and result in an H3O plus and a Cl minus. But you can also just write it as HCl dissociating to an H plus and a Cl minus. Okay? I prefer this way here. I don't need to be reminded constantly that the water molecule is interacting with that hydrogen ion. I know that that's the case. All ions in aqueous solution have to have a huge amount of water molecules interacting with them. Okay. Now, we have a name for this chloride ion in this case. This here we call the acid. All right. And the component, which is now the acid without the hydrogen, we call this the conjugate base. The conjugate base. All right. So we can refer to this as a conjugate base acid pair or conjugate acid base pair. All right. And again, the difference is always just one proton. Right? So here's an example, HCN, this is an acid, and its conjugate base is the Cn minus ion, right? The cyanate ion. So hydrogen cyanate and then the cyanate ion. You could also, even though this is a base here, and this over here is water, and we don't think of water as an acid, but if you can refer to water as an acid, and then this, the hydroxide ion, as its conjugate base. Because again, these two just differ by one hydrogen. Now, we don't generally think about the water as an acid, like I said. However, this kind of a reaction here where HCN takes or is giving a hydroxide giving a hydrogen ion to hydroxide ion to form H2O, right, isn't really a reversible reaction, but you can have reversible reactions where the water molecule will give a hydrogen ion to the Cn minus ion, and so water can act like an acid when the definition of an acid is it donates a hydrogen ion, okay? And we'll see other examples of that as well. So let's see if we can come up with our conjugate base, conjugate acid pairs for this table here. Ready to help me out, Camille?
Yeah.
All right, here we go. So, conjugate acid, HCl, what would the conjugate base be?
Is it chlorine?
Uh-huh. It's the Cl, but it has to have the minus charge on it, right?
Okay.
Because we've removed not just the hydrogen, but the hydrogen ion, H+. All right, so if NH3 is the base, what is the conjugate acid? So going from HCl to this...
Just NH3?
Well, NH3 is the conjugate base. So then the acid has to have more hydrogen, right?
Was it NH3 plus?
Well, it's NH4 with that plus charge.
Okay.
All right. So going from the acid, HCl, to the base, we had to remove an H plus. Going from the base to the acid, we had to add the H plus. Okay, good. So now this one here, conjugate base, if we start with this acid, which is acetic acid, HC2, H3O2, what would the conjugate base be over here? If we have the acid, we remove what?
Hydrogen.
That's right. And so we're left with?
C2H3O2.
With what kind of a charge?
Minus charge.
With a minus charge. Very good. So Cn minus, our conjugate base, what would the conjugate acid be if that's our conjugate base?
Cn plus 1.
Well, what does it we add? We have to add something to,
We have to add nitrogen.
we have to add a hydrogen. That's right, hydrogen, right? So it's going to be HCN, right? And the charge
And plus.
is not going to be negative anymore because like here, the Cl minus went from Cl minus to HCl. It didn't go HCl plus because we just add one positive charge and that goes from minus to neutral. So this is going to be HCN. Does that make
Okay.
sense?
Yes.
Okay, last one. What?
That'll be
Go ahead.
F minus.
F minus. Very good. Excellent. Good job. So, how many of the following pairs are conjugate pairs? So why don't you guys look at this one, see if these are conjugate pairs. Are these conjugate pairs? Are these conjugate pairs? So we have, how many of these are actually conjugate pairs? What do you think? You could write a little answer down there in the public chat if you wanted to.
Well, I know the second one is for sure.
Yes, good. How about this third one?
I feel like it should be.
Okay. How about the first one?
No.
No?
Yes, I have no idea.
So again, our conjugate base, we just add a hydrogen ion. So here's the Cn minus, Cn minus. So if I write down here, Cn minus, and I add a hydrogen ion, the result is going to be what? If I combine these together, I'm going to have HCN, and then these charges are going to cancel each other out.
Oh, so there's 3.
Okay, so there's first one, that's okay, this one's okay. What happens, what's going on here? S2 minus, S2 minus, I just add what? What do I add, Camille?
2 hydrogen.
Well, if I have,
Oh, no, just 1 hydrogen.
what's that?
Just 1 hydrogen.
Yeah, you always just add one because that's what the definition of the acid is. The acid in its conjugate base, or the base in its conjugate acid, is just one hydrogen ion difference. So if I just added one hydrogen ion, I would have what? What would my resulting product be here?
HS2.
H, S, and then what is the resulting charge? If I have a -2 here and a positive 1 here?
Plus, no, negative.
Yeah, HS negative.
Oh, there's only 2.
Right. So that there would be a conjugate pair, but not this. This is 2 hydrogens coming on and off. Okay, very good. Amphoteric. Amphoteric is a word that means the molecule can go both ways. It can both give a proton and it can receive a proton. And this compound here is an example of that, right? HS minus can give a proton by going this way and become the S2 minus ion. But HS minus can also take a proton and become H2S. All right? So can you see how this can give a proton and become S2 minus, take a proton and become H2S? And that property is called amphoteric. Okay? And we kind of introduced this word because a very important chemical, water, is amphoteric. All right? So here's water by itself. And you probably have already kind of realized this, but never cared to think much of it. But I can add a hydrogen to water. What's the product there, Brielle, if I add a hydrogen to water? What will my product be?
H3O.
That's right, H3O plus. And if I remove a hydrogen, Brielle, what's my product?
HO.
That's right, the OH minus charge. Okay, and I got to write the H plus ion that I've removed there. Very good. So, water, an amphoteric material. All right. So, we want to write a reaction now in which HCO3 minus is an acid, and it reacts with OH minus. Okay? H3O minus is an acid reacting with OH minus. So, that's going to look like this, right? That's going to look like HCO3 minus reacting with OH minus. Now the question is, who's going to give the proton and who's going to take the proton? Who's going to be giving up a proton in this reaction, Camille? And how do I know who's going to be giving up a proton?
Oxygen.
Well, it's either this species or this species. This is a bicarbonate ion, and this is the hydroxide ion. And the answer is in the question up here.
OH, the hydroxide ion.
All right, which one is acting as the acid? Can you tell by looking at the question which one is acting as an acid?
HCO3.
That's right. So that means that one is going to be giving the hydrogen, donating a hydrogen. Okay? So if this donates a hydrogen to the hydroxide ion, what will the result be?
CO3, H2O.
It'll be CO3 and H2O. Is that what you meant?
Yeah.
Okay, very good. CO3 2 minus and H2O. So this hydrogen, we were told that this was the acid, right? Therefore, this hydrogen is going to be donated to this material, this compound over here. And if I look at this and think about what it's going to look like with another hydrogen, I can remember it's water. And what's going to be left behind then is the CO3 with an extra negative charge, right? CO3 2 minus, or the carbonate ion. Okay, very good. Here we go. Let's write a reaction now that shows HCO3 is a Bronsted base when reacted with H3O plus. Brielle, do you want to help us out with this one?
Yeah, so since it's the base, the H3O plus will donate its hydrogen to the HCO3 minus.
And what will my products be?
It will become H2CO3 and then water, so H2O.
Okay, very good. Excellent. So, again, we were told that this time this compound was going to behave as a base, which means it's going to be accepting the hydrogen. That means this one is behaving as the acid. All right? So, Camille, if this is my base, what is its conjugate acid? Where is its conjugate acid?
Would it be the CO3?
This is the HCO3, and if this is the base, then it
Oh, the acid.
would have to have more hydrogens, right?
Yes, so it would be the H2.
That's right. Very good. And if I said the water here is the conjugate base, then what is the conjugate acid for water, Camille?
Is it just the H? It's just HO.
No, this has to take a hydrogen. So if this is acting, if we're saying that this is a base, then
The H3O.
it has to be H3O plus, right? So this is its conjugate acid. And if you think about this reaction going backwards like that, in this process here, this one is acting as an acid, going in reverse, because it's giving the hydrogen to the water and resulting in H3O plus. So going left to right, this is behaving as the acid, and going from right to left, this chemical is behaving as an acid, and water is behaving as our base. Okay. Excellent. So, how many of these compounds are amphoteric? How many of these compounds are amphoteric? Amphoteric means it can give and receive. What do you think, Brielle?
I am not 100% sure, but I'm thinking the last two.
Okay.
be-
What made
Yeah,
you think that?
I don't know, just the minus signs on them.
Yeah, yeah. That's a good sign that, hey, they have a negative charge. They could probably take a positively charged ion. Okay, that's right. Whoops. What did we do wrong there? HSO4 minus H2. Oh, we were tricked. We were tricked. Okay, so here is why we were tricked. And let's have a little conversation about that. Some acids are strong acids. Let's make a list of our strong acids for those at home who can't remember. I'm sure you guys can remember, but we'll make a list of our strong acids. Our strong acids are HCl, HBr, HI, HNO3, H2SO4, HClO4, and HClO3. So those are our strong acids. So what that means is, again, a strong acid. You put it into solution, into water, H2SO4, for example, and up here, it completely dissociates. So the H plus ion results, and the HSO4 minus ion is there, is the conjugate base of this compound. All right? So here's the acid, and here's its conjugate base. And so because this is the conjugate base of a strong acid, the HSO4 minus, in solution, you're never going to get that hydrogen to go back on because it's not reversible. The only reason we know it's not reversible is because it's a strong acid. So because HSO4 is the conjugate base of a strong acid, it's not reversible. That's going to be the same for all of the conjugate bases for our strong acids. Let's make a list of the conjugate bases for these strong acids. Camille, can you make this list for us? Here are our strong acids, 1, 2, 3, 4, 5, 6, 7. Now let's make a list over here of the conjugate bases for these strong acids. Let's make it in
Um,
same location. So.
is chlorine minus.
All right, Cl minus, that's the conjugate base for HCl.
And then H2SO4. Would it be HSO4?
Very good, HSO4, and then the minus. What do you?
For nitric acid,
Uh-huh.
would you just take away the hydrogen, so it would just be NO3?
NO3. What else? What am I missing there?
Minus.
Minus. Very good. Keep going. You're on a roll.
I'm gonna do the ones that I know. I think I can get. The hydrofluoric acid. Oh wait, there's not. Hydrofluoric acid. Well, I'm working on it.
In all of them, all we have to do is remove the hydrogen and then put a negative charge on what's left over, right?
Yes. So HClO4 would just be ClO4 minus.
Good. ClO4 minus.
And then HBr would be just bromine minus.
All right, the bromide ion. Good.
What acid is HI?
Hydroiodic acid.
So that's just I minus.
I minus. Very good.
And then ClO3 minus.
Yes, that's right. That's right. So, these are the strong acids. And these are the conjugate bases for the strong acids. Okay? All right. Excellent. So, moving on. Acid strength. We know this pretty well already. If there is a strong acid and it lets go of its hydrogen, the conjugate base won't take that hydrogen back, right? If it's a weak acid, however, and a hydrogen is released, the conjugate base will take the hydrogen back. In fact, if you look at a compound like acetic acid, or that's the acid in vinegar, right? HC2O3, wait, C2H3, sorry, H3O2. HC2H3O2, this compound releases a hydrogen because it is an acid, and the conjugate base for this is C2H3O2 minus, all right? However, the reversing arrow has to be drawn because hydrogen ion and the acetate ion will find each other relatively quickly and come right back. All right? In fact, at any one given moment in a solution of acetic acid, only about 1 in every maybe 1,000 molecules is separated. Okay? So it's not a strong acid. It's actually relatively strong for the weak acids, but it is a weak acid. All right? So when you're mixing a strong acid and a weak acid, the weak acid will always behave, or the conjugate base of the weak acid will always behave as a base. Okay. Also, we just made this beautiful list here of strong acids and their conjugate bases. Okay? And we also just had a problem where we looked at HSO4 minus and said that that compound, HSO4 minus, could not behave as a base. Could not behave as a base. That means it can't accept a hydrogen. And in reality, none of these conjugate bases of strong acids can behave like bases very well. Now, why do you think that is, Brielle? I mean, why is it that we should know that if it's the conjugate base of a strong acid, that it's not going to be able to take the hydrogen back?
Since it is a strong acid,
That's right.
I don't know.
Since it is a strong acid, you put it into water, it's always going to be dissociated. It's never going to go back. So that would mean that if these ions were in water, they would never take a hydrogen ion back. Okay? So that allows us to think of our conjugate bases and identify how strong of a base it would actually be. So if you take something like HClO4, that's a really strong acid, and therefore ClO4 minus is not a very good base, right? And that makes sense. I mean, we're basically saying, when we say HClO4 is a strong acid, we're saying ClO4 minus is not a good base, right? Because HClO4 being a strong acid means they want to separate. ClO4 minus not wanting to take a hydrogen, that means it's not a good base, because bases take hydrogens. On the other hand, if we look at a compound like NH3, it's not a very good acid. It doesn't like to let go of its hydrogen very well. Therefore, if you find NH3 that has a hydrogen removed, it would be NH2 minus, and NH2 minus then becomes a very strong base, right? If you put NH2 minus into water, all of it will take a hydrogen and form NH3, okay? So if you have a strong acid, you know that its conjugate base is a very bad, weak base. If you have a weak acid, you know its conjugate base is going to be a very strong base. Because, like we said, when you say a weak acid, it means it doesn't want to give rid of the hydrogen very much. Okay, so we see that there's this relationship between how the strength of an acid and the strength of its conjugate base. So, here is a scenario. If we take something like H3O plus and combine it with CO3 2 minus, all right, and we're given this information down below in terms of increasing strength of acid. So water is the weakest acid that's listed here in this list, with H3O plus being the strongest acid. Now, what does that mean, the strongest acid? That means that H3O is going to behave like an acid, apparently, strongest acid. But what does an acid do, Brielle? What's the job of an acid?
Donate its proton.
It donates its proton. That's right. It gives its proton. So H3O plus is the one that will want to give the proton more than any other compound. I mean, more than any of these other compounds here. So if we're looking at H3O plus and it reacting with CO3 2 minus, and then we look at the products over here, here we can see that H3O plus is acting like an acid with the CO3 2 minus. It acts like an acid because I can see that it gives up a proton to form H2O plus. I can also see that the CO3 2 minus is behaving like a base. It's taking that proton and forming the bicarbonate ion. All right. So we have the carbonate ion taking a proton, behaving like a base. In the reverse reaction here, which one of these two compounds here, Camille, see these two compounds on the right, which one is behaving like an acid and which one is behaving like a base, assuming that the reaction is going back towards the reactants? Which one is behaving as an acid? Go ahead.
Is H3 the acid?
The HCO3 minus here?
Yeah.
That's right. It's behaving like an acid. Again, if I'm looking at these as our reactants heading back this way, I can see that it starts off as HCO3 minus, and it gives up the hydrogen. Therefore, this one is behaving as an acid. So in the reaction heading to the left, this is behaving as the acid. In the reaction going to the right, what do you think, Camille? Camille, which one's behaving as an acid if we're going to the right? The CO3 2 minus is behaving as the acid?
You sounded questionable when you said that, so I'm gonna say H3O is for that.
Well, we could just look and see in terms of either donating a proton, or accepting the proton, right? What is CO3 2 minus doing here? Is it accepting or giving the proton?
Giving.
Well, what does it end up as?
Oh, no, it's accepting.
It's accepting. So does that make it the acid or the base if it's accepting a proton?
Base.
Yeah, the base.
Acid.
No, the base.
Okay. Base.
An acid is the hydrogen ion donator, right? It has the hydrogen ion, and therefore it's donating.
Okay.
So here we have H3O plus behaving as an acid on the left side of the reaction, and the HCO3 minus behaving as an acid on the right side of the reaction. And so we can identify the preferred direction of this reaction by looking for which one of these acids, H3O plus or HCO3 minus, are the stronger acids. Which one is the stronger acid? Okay? Well, H3O plus is on this scale here, and it says it's the strongest acid. HCO3 minus isn't on the scale here, but the H2CO3 is on the scale, and it's not as strong as H3O plus. So we would say that this reaction is going to lean towards the right here, because H3O plus is the stronger acid. Okay, now this next one. You're going to help me out with this one, Brielle. We have our reaction heading to the right and our reaction heading to the left. We want to identify first, going to the right, who's behaving as an acid, and then second, going to the left, who's behaving as an acid. All right? What do you think, Brielle? Who's behaving as an acid going to the right?
Okay, going to the right is NH4 plus
Good.
because it's donating its hydrogen.
And becoming NH3. Very good.
Then going to the left, it would be the H2CO3 because it's donating its hydrogen.
Okay, excellent. So now we can decide which one is a stronger acid with our little scale here, and we would show which direction we would expect this reaction to want to be heading. Which side has the stronger acid? The left side or the right side?
The left side.
The left side, NH4 plus?
Oh, wait, I meant right side.
Okay,
I'm thinking of, going to the left. But yeah,
that's right.
it's the H2CO3.
It's going to be heading to the left because the H2CO3 is on our list as the stronger acid than the NH4. All right, your turn, Camille. So we have a chemical reaction here. We want to identify which one's behaving as an acid as we head to the right in this reaction. Sorry, yeah, head to the right. And then we're going to identify what the acid is heading to the left. What do you think, Camille? Which one is the acid amongst these two right here?
The
HCN. We can tell it's the acid because it gives the hydrogen ion to the Cl here. And then Cn minus is left alone. Going back the other way, which one is behaving as an acid?
HCl.
The HCl. So we said that HCN and HCl are both behaving as acids. And now we have to think and see if maybe our scale helps us. Which acid is stronger, HCN or HCl? What do you think, Camille?
HCl.
You think HCN is stronger than HCl?
Well, HCl isn't on the scale.
Yeah, that's kind of a pain in the neck, huh? HCl is not on the scale. It's like they want us to know already something about HCl and its strength. Maybe we should. Do we know anything about HCl already?
It's one of the strong acids.
It is one of the strong acids, and HCN is not. So what?
So I'm going to say HCl, actually.
Yeah, the HCl is the stronger acid. So is this reaction going to want to prefer to go to the left or to the right then, Camille? It's going to want to go away from the stronger acid, right? The stronger acid is going to behave like an acid stronger. So it's going to the left here. Excellent. Very good. Wonderful job. Okay, so we're going to skip this one here, but same idea. You just have, you look at your strongest one and see which one is going in the right direction. Now we're going to talk about periodic trends for binary acids. Binary acids. We should probably have a little bit of a review really quick on what a binary acid is. Don't you think? Some people out there probably can't remember. I'm sure both of you guys remember what a binary acid is, but some people might not remember what a binary acid is compared to, well, I don't know. Do you guys remember what the other kind of acid is, Brielle? Binary, and then what's the other kind?
I have no idea.
Okay. There's binary acids, and then we have oxy acids. Does that ring a bell at all?
Nope.
Nope. Okay. All right. So binary means two, just two elements in this acid. Okay? Only two elements in this acid. Now, HCl, that's an example of a binary acid, right? HF is an example of a binary acid. What else is there? H2S, right? Basically, you just take some element and put hydrogen, one or many, in front of it to form a compound, and the result is what we call a binary acid. Okay? And the strength of these binary acids increases as you head to the right and then down on the periodic table. Okay? So, looking at our periodic table here, take an atom, or an element, fluorine, add a hydrogen, right? The HF, that would be a binary acid. Do the same thing with HI, or iodine, add a H to it, HI. So, HI. And then which of these acids would be stronger, Brielle? HF or HI? HI, that's right. Because strength of acid increases as you head to the right and then down. And these are for binary acids. Binary acids. Okay, now, we should also have a little bit of a reminder about what strength means. I know we've already kind of been talking about it the whole time, but we don't want you to be confused into thinking strength meaning it's going to damage your skin or you know, poison you or something like that. Okay? Strength, again, just refers to the degree to which it will dissociate when placed in water. All right? Okay, so here's a question for you. Camille, tough question. I have H2S and H2SE, hydrosulfuric and hydroselenic acid. These two acids right here. Which one is a stronger acid?
Well, if I had to guess, I'm going to say H2SE.
Okay, and why would you be guessing? Why? I mean, what does this figure help us out here? That little picture right there?
Because SE is lower.
Yeah.
Down.
Very good.
Further.
That's right, in the periodic table. And that's why it's a stronger acid than H2S. Okay? Very good. I'm going to talk a little bit about why that's the case, why we see this trend. Okay? If we think about hydrogen ions being on atoms like nitrogen, oxygen, or fluorine, okay? If a hydrogen ion is on a nitrogen and you remove that hydrogen, it disrupts the compound, and the compound will have a minus charge, right? If you think about, so let's write this out for ourselves. I'm going to make this a little bit smaller. If I have compound nitrogen with 3 hydrogens on it, and I want to remove a hydrogen and leave behind NH2 minus, all right? This compound here is not very stable. It's not very stable, all right? It wants to have that hydrogen, okay? If I have H2O, again, oxygen with hydrogens on it, and I remove that hydrogen ion, again, it's not very stable, all right? If I have HF and I want to remove a hydrogen ion and make F minus, it's not stable, but this one here is the most stable. Therefore, of these 3, HF will be the strongest acid. Okay? So strength of acids, if these are all 3 being compared as how good of acids they are, will depend on the stability of the conjugate base in solution. All right? And that's because of the ability for water molecules to stabilize these charges. Going down the periodic table, HF, HCl, HBr, HI, as you release, if I have HF, HCl, and HI, and Brielle, remind us, which of these is the strongest acid? HI is the strongest acid. That's right. And the reason why is always because the resulting products are more stable. So what is more stable in solution? The fluoride ion, the chloride ion, or the iodide ion, Brielle? That's right. The iodide ion is more stable. Now, I'm going to tell you why it's more stable. The reason why it's more stable is because it's larger. And because it's larger, more water molecules can surround it to help stabilize its negative charge. Whoops, hydrogen. So the hydrogen ends of water molecules can get around this iodide ion and stabilize it. So when HI is in solution, it's easy for the water molecules to remove the iodide ion from the hydrogen. All right? As you get smaller here, the fluoride ion is so small, you can't get enough water molecules around it to give enough stability. And so it's the least stable, and therefore HF is the weakest of these acids here. All right? So this trend of strength of acid heading to the right and then going down has to do with stability of the resulting counter ion, we call it, or the anion, when the acid forms. Again, this is for binary acids, just elements with hydrogens on them. So here it is. Which one of these is a stronger acid, H2S or H2O? Camille, which one is a stronger acid, H2S or H2O?
H2S.
That's right. Very good. Lower down in the periodic table. Which one of these is a stronger acid, Brielle? CH4 or NH3?
H3.
NH3 is our stronger acid. Now, you know, if you think about CH4 and NH3, nobody thinks about them as acids in general. But there's all sorts of chemistry that can occur. So, and in this chapter, we're going to be treating anything we want to as an acid. And so that's right. The CH4 is going to be, sorry, the NH3 is going to behave as our stronger acid, and we can know that by its location on the periodic table. HF and HI, Camille, which one is a stronger acid?
I.
HI. Very good. Now, in terms of strength of acids for oxy acids, and we better have a little review because it didn't sound like we're very familiar. We can't remember very well about what oxy acids, why they're called oxy acids. But I'll tell you, they're called oxy acids because they contain a special element. Which element do you think that is, Camille? Very good. Excellent. So elements that contain, or acids that contain oxygen are oxy acids. Now, water is not really considered an oxy acid, right? But when we say contain hydrogen or oxygen, it's that the element, so for example, nitrogen in HNO3, an oxy acid, the nitrogen is surrounded by oxygen atoms, right? And then the hydrogen is connecting to the polyatomic ion by an oxygen atom. H3PO4, phosphoric acid. The phosphorus is in the middle, 4 oxygens, right? And then 3 of these oxygens have hydrogens on them, right? And again, the element in the middle is connected to the hydrogens through the oxygens. All right? So these are oxy acids, and the strength of oxy acids increases as you head to the right and up for the element that's in the middle of the oxygens. Okay? So, 2 acids, H3PO4. Oh wait, did we go over this already? Oh, also you increase the strength of the atom or of the acid as you increase the number of oxygen atoms that are on the central atom. Okay? So here's an example for that. H3PO4, and I'll draw it here for us. H3PO4 and H3PO3. Here's H3PO4, and I'm going to draw H3PO3, phosphorus, 3 oxygens, 3 hydrogens over here. Okay? In this case, H3PO4 is going to be our stronger acid because it has more oxygens. All right? Now, where does this come from? Why is it that more oxygens results in a stronger acid? And why is it that as we go to the right and up for this central atom, we make a stronger acid? Okay? So to the right and up is basically following the trend of electronegativity, right? The most electronegative atoms up here to the right and up. So let's think about what's going on here. In an oxy acid, you have a central atom that is, again, surrounded by some oxygens. And the hydrogens are on those oxygens, 1 or 2 or all of them. And if this thing is going to behave as an acid, it has to release a hydrogen ion. It has to release a hydrogen ion. So that means that if this is going to release a hydrogen ion, then one of these oxygens, right, in this case this one, is going to end up with a negative charge. A negative charge. And the strength of the acid depends on the water's ability to stabilize this negative charge. And in this case, if this negative charge is here, if X is electronegative, then it can pull that negative charge in towards itself. If X is more electronegative, like chlorine or bromine or fluorine, right? So a more electronegative X makes it easier to stabilize that charge because some of that electron density will be pulled in here. All right. Another thing that we introduced last semester was what we call resonance structures for this ion. Okay? Resonance structures, you probably don't remember very well, but it's essentially where we take our negative sign and we can distribute it to a different location. So now I've taken my negative sign and I've moved it over to this oxygen here. So this should really be a double bond here. So I have multiple resonance structures that can occur, and that movement of electron density around the molecule, it also results in some stability. Okay, it can occupy that negative charge, and therefore that ion will be stabilized when it's in water. And all of this is helpful in making this a stronger acid, right? Because again, the strength of the acid depends directly on the ability of the ion to be stabilized in an aqueous solution. So, we see the trend and understand it now because A, we see that the central atom's electronegativity will draw electron density away from wherever that negative charge is formed, and that will stabilize the acids, make it stronger. So our trend follows electronegativity. And then our second influencer of the strength of acid is the number of oxygens. Because if we have more oxygens, we have more resonance structures, and the electron density can move around into different places. All right, so here's our two acids, H3PO4 and H3PO3. Brielle, can you help us? Which one of these is going to be a stronger acid?
PO4.
The H3PO4. And we can tell because why, Brielle? How do we know?
It has more oxygens.
More oxygens. Very good. H2SO4 and H3PO4, Camille. Which one of these is a stronger acid? We have to bring up our periodic table.
Oh, H3SO4. Right, H2. Whoa. H2SO4.
H2SO4, that's right. H2SO4 is going to be our stronger acid. Now we also know something about H2SO4, don't we?
Oh, it's one of the strong acids.
It's one of the strong acids. H3PO4 is not. So that was a gimme for that. But also, we can use the periodic table to know that. Okay, so Brielle, H3ASO4, H3PO4. Which one of those is a stronger acid?
H3PO4.
All right, very good, because phosphorus is more electronegative, higher than that of arsenic. Camille, which one is stronger acid here? H2SeO4 or H2SeO3?
H2SeO4.
Very good. More oxygens around it. Excellent. Okay. So, ions that result from acids, oxy acids, right, have a degree of basicity. They can act as a base, again, depending on how strong their conjugate acid is. All right? And what this means is So let's go back to this list here. H2SeO4, H2SeO3. We said that H2SeO4 was a stronger acid. So my question is, which one of these compounds is a stronger base? Start over. HSeO4 minus or HSeO3 minus? Which one of these is a stronger base? Okay, Brielle, do you want to help us out with this one?
So is it the stronger the base, the weaker the conjugate acid? Is that what we were talking about before?
That's right. Very good.
So would it be the HSeO3 minus?
All right. Because if this compound is going to behave as a base, it means it's going to take a hydrogen and form H2SeO3, right? If this thing is going to behave as a base, it's going to take a hydrogen and form H2SeO4. And we just said that going backwards here, this one would be our stronger acid, right? Stronger acid, that's what we set up here. This is a weaker acid, making this one over here our stronger base when compared to this one, right? Very good. Okay, so because this one is our stronger acid when comparing these two, that means this one down here is a stronger base than that one there. Okay? All right, so that also means that if we take a salt like this salt here, Na2CO3. This is a salt. Solubility. Do you guys remember solubility at all? That was a long time ago. Does either of you know if this is soluble when you put it into water?
Yes.
It is? How do you know?
I was just guessing.
It is. It is. And one of the rules was that compounds that contain sodium are always soluble. Always soluble. Therefore, we place it into water, and what will result? Camille, can you tell us what ions will result?
No.
Well, what are the ions that are here in this compound?
Well, there's Na2CO3.
We got the sodium ion. Na2CO3 is our compound. And in there is the sodium ion, and the other ion is the what? The CO3 2 minus, is that right? All right. So, when I put Na2CO3 into solution, I'm going to get 2 sodium ions and a carbonate ion. We know that, old stuff. This compound is soluble, we decided. Sodium is always soluble, so that's what's going to result. Tell me, Brielle, is this, see this compound right here, this looks like, because of its negative charge, that it could be a conjugate base, right? If this was a conjugate base, what would its conjugate acid be, Brielle?
Would it be HCO3?
Very good. HCO3. What would the charge be left on it?
Minus.
Minus charge. That's right. And we could even give it one more hydrogen and form H plus, that's going to be an H plus ion, and then make it H2CO3. Now, tell me about the strength of this acid, H2CO3. Is that a strong acid, do you guys know? Camille, what do you think? Is that a strong acid? Was it on our list? Was it on our list? Where's our list of strong acids? Do you have our list? Did you write that down?
I should have. I will.
Not on my list.
It's not on the list, is it? There it is. Strong acids. So H2CO3 is not a strong acid. And so that means if this is a weak acid, it means that CO3 minus will be what kind of a base, Riel?
A strong base.
It's going to be a relatively strong base. That's right. It also means that HCO3 minus might not be as strong as CO3 minus, but it will be relatively strong as well. So because we know that this is a weak acid, and we therefore know that this is a strong base. And when you put that strong base into water, it's going to take hydrogens away from the water. So when I put Na2CO3, salt, into water, the sodium ion and the carbonate ion result. And then when the carbonate ion's around, it begins to take hydrogens. And it's not going to take hydrogens H+. And if it's around, they will, but usually those are going to be in the form of just water. And so you're going to result in HCO3 minus and the hydroxide ion. All right? And then this could take another hydrogen from another water molecule and result in another hydrogen ion. So this compound here becomes a strong base. No hydroxide in it, but when the carbonate ion gets into solution, it takes the hydrogen from water and results in the hydroxide ion. Okay. So I think that is a good place to stop for today. Next time we'll talk about what we call Lewis acids and bases a little bit. And then we'll move on and talk about different ways that water can kind of auto-ionize, how we define pH. All right. Some of this will be review, but some will be new. Okay, very good. Thank you so much for being here today. And we will see you again on Monday, right? Monday. Any questions? You bet. See you later.
You are currently the only person in this conference.